training events that training and promotions that Nicole mentioned earlier. So that motor madness, I'm getting a free capacitor with every motor. You know, if you're replacing a PSC motor, you need to go ahead and replace the capacitor with that motor. So that's a pretty good deal. And your vacuum pump, I don't have a poll set up for this or anything, but if we were in person, I would just ask this. Every time you use your vacuum pump, you should replace the oil in your pump. So that's a pretty good deal too. I know that a lot of people don't really change the oil in their pump until it starts to look like milk, and that can be problematic for you. So anyway, I'll go ahead and get started on the class that I'm actually here to deliver. So yeah, my name is Wade Hadaway. I have been with Ruud for about 6.5 years. But have been working with Tropic for that same amount of time. And I have prior to this role, I did teach in technical education, and prior to that, I was out working in the field. I've just done just about every job on the residential side of this business that you can do, and I have done just about everything the wrong way that you can do wrong. So I have learned not only I went to technical school, but I also way before that, for many years before that, just sort of learned OTJ and did a lot of things the wrong way, did a lot of things the right way, but didn't really know why that was the right way to do it. So today we're going to talk about airflow. We're going to talk about how to measure airflow. We're going to talk about how to properly set up your blower to deliver the airflow that's needed for whatever matchup that we're working on. And then we're going to round things out by walking through how to actually measure and calculate the cooling capacity that your system is operating under. So the last thing we're going to talk about today is we're going to go through what numbers we need and how to plug them into a formula to tell you exactly how many BTUs a particular system is removing from the conditioned space. And that can be really helpful in solving problems and or diagnosing issues, especially if you have a customer, homeowner, property owner, tenant who is complaining that the system's not keeping up. Right, we all know that when you do your load calculation, that the load you're sizing to is not necessarily the extreme temperatures. So things can be a lot warmer than the system is really designed for, and sometimes that can cause issues where the system just runs all day long. It doesn't really satisfy till late at night. Instead of just telling your homeowner or your customer, hey, it's doing all it can do, you can actually prove it. Is it doing all it can do, or do we need to look at some things? So yeah, this is part 2 of a 4-part series that we're doing here this spring. Next week we will do a class on compressors, and really that's going to focus a lot on what causes compressors to fail in the field. We will talk about some troubleshooting. We will talk about some diagnostic techniques. And then in part 4, when we get to electricity and wiring, we'll also talk about how to diagnose and test compressors as part of that electrical class. Before we get started, I wanted to take a quick poll just to sort of see where we are as far as experience level. So Nicole, can you throw that poll up? So how many years experience, everybody on this call, how many years experience do you have in the industry? are you relatively new, right? Are you just sort of dipping your toes into the pond, as it were? Or are you an old timer? You've been in 10 plus years or anywhere in between? Look, if y'all would just take a minute, and this is really just to sort of give me an idea of sort of where we are as far as attendance on today's class. I'm always curious to know how long everybody's been sort of working in the HVAC industry and in this field. I'll probably ask a poll about your job or your particular role in an upcoming class. It seems like in a lot of classes I get a lot of installers. I mean, I get a lot of service techs, but I don't get a lot of installers a lot of times in classes, and I think sometimes that can be problematic. Okay, so we got over half have been in for 10 plus years, so that's awesome. We got quite a few in the 5 to 10 range, and quite a few in the 1 year or less. So awesome. Well, welcome to the Great Trade. It's been good to me. It's been good to I'm sure a lot of other folks on this call. So thanks for taking the time to do that. So airflow. Airflow, and I've said this a lot. If you've been in any of my classes, you probably heard me say that airflow is the most important thing that gets looked at last when somebody has a problem with a piece of equipment. Typically, when someone goes out to do a startup, or they go out to do a service call or a maintenance or whatever, they hook their gauges up, they look at their pressures, they look at the charging chart to see if the charge is right, without ever really verifying or checking airflow. And if the airflow through really both of your coils, your indoor coil and your outdoor coil, if your airflow is not right, not a whole lot we can do about the outdoor airflow other than making sure that the outdoor coil is clean. But if the airflow through your indoor coil is not correct, then the charging chart is not relevant. So it doesn't do us any good to adjust the charge if we haven't verified that we have the right amount of air moving through our indoor coil. So the most common way to measure that airflow is by checking the static pressure, and the static pressure is the pressure that the air moving through the duct applies to the sidewall of that duct. So if you think about like a canvas, like a sock duct, or even a balloon, right? The pressure of the air pushing against the sidewall of the duct, right? The static pressure is what blows up that sock duct, makes it round or cylindrical. There are a couple of other pressures that we can measure in the air. There is the velocity pressure, which is really just the speed of the air moving through the duct. And then there's the total pressure, which is really, we just add the velocity pressure and the static pressure. For our purposes, we're much more concerned with static than we are with velocity and total pressure when it comes to making sure that we're moving the right amount of air. And when we start looking at blower tables, you'll see that that's all driven by the static pressure. Right. So again, the static pressure is the pressure that is being applied or pushed on the sidewall of the duct on the inside of our duct. And so another term that we're going to talk about a lot is cubic feet per minute, right? And really that just tells us how much air is that blower moving. And the reason I have that milk crate there is that is a really good visual representation of a cubic foot of air, right? And really a milk crate, I think, is like 13 by 13 by 12. but it's close enough, right? So a cubic foot is 12 inches wide, 12 inches long, 12 inches tall. So 12 by 12 by 12 is a cubic foot. And when we think about just say 800 CFM, I think about 800 milk crates of air per minute, right? 800 cubic feet per minute of air moving through the ductwork. And when I think about that, and I look at ductwork, or I start measuring static pressure, if we've got a rated amount of air in cubic feet per minute that we've got to move through some ductwork, and the more restrictive that ductwork is, the harder it is to move the air through it, quite simply, right? So a lot of times it's not just about how is the equipment configured, but it's about how is the ductwork laid out, and that can be as challenging as anything else, especially if we're doing retrofits or change outs, right? So the blower in our indoor piece of equipment, whether it's a pull through, like is in an air handler, right? So in an air handler, our blower motor and our centrifugal fan or our squirrel cage is on the is in front of our coil. So we pull the air through the coil. Typically in a gas furnace, our blower is in front of the coil. And so we're pushing the air through our cooling coil in a gas furnace. Typically, not always. So we have got a pressure differential there, right? So we've got a negative pressure that is created to pull the air into the blower or into the blower wheel. And then the positive pressure is the air being pushed from the blower. So we've got a negative pressure and a positive pressure. And that pressure differential is what causes the air to get pulled into our squirrel cage and then pushed out. And it doesn't really matter. It affects the air as far as which side of the whether it's our coil is on the negative or the positive side, but it doesn't really matter. We have to create that pressure differential or we're not going to move the air. And every fan does it. Any pump does it, right? It creates a negative and then a positive. So in that airflow, whether it's in the return or the supply, any resistance creates a pressure drop. And that pressure drop is typically caused by friction or turbulence. And that friction could be the air moving through our cooling coil. The friction is the air moving through registers and grills. The friction is and/or turbulence. The friction is also just the drag on the sidewall of the duct. So as the air is moving through the ductwork, everything in that system is slowing that air down and making it harder for the air to move through the ductwork to get either to or from the conditioned space. So materials, right? Whether you're using flex duct or hard pipe, and flex is super common here in the Southeast, right? Some northern areas, some northern territories, some of my colleagues that work up north, everything is still all hard pipe. But for us, right, I covered 5 states here in the Southeast, and it's almost all flex. So, and flex duct is great as long as it's run properly. And we're going to talk a little bit about that too. But filters, coils, heaters, right? Everything in that airflow is going to cause a pressure drop. And everything in the equipment that's in the airstream is going to cause a pressure drop. And so we have to account for that. If you're as part of your, I don't know, a service call, a change out, whatever you're doing, if part of that is to upgrade IAQ, right? If you're going to add some filtration, if you're going to add a UV light, if you're going to add anything to that airstream, you need to make sure that you're not causing issues with your static pressure. And if that's the case, you might need to expand or add some ductwork. Not saying don't sell IAQ products at all. I'm just saying if you do, you might have to factor in adding some ductwork. So yeah, duct material, talked about this a little bit, right? So the difference between a piece of flex and a piece of hard pipe is pretty obvious when you're really looking at those materials, right? So the flex duct is obviously flexible. You got to work pretty hard to run your hard pipe in a sort of serpentine layout like you can pretty easily do with flex. And if you look at the inside of a piece of hard pipe versus a piece of flex, you can see how flex duct can cause more friction and turbulence just from that spiral wire that runs, that sort of holds the interior liner open. A 16-inch flex run moves about the same amount of air as a 14-inch hard pipe. So if you're looking at some plans and you've got some ductwork that's spec'd out for hard pipe, you're going to have to make sure you upsize your flex when you run it, or else you're going to run into potentially going to run into some static pressure issues. The duct system and the way those ducts are run and laid out has a significant effect on a lot of things, right? It affects many things, including the comfort and operating sound. Okay, so comfort wise, we don't want to set or we don't want our registers to blow directly on your customer who maybe is sitting in their favorite chair watching TV, unless that's what they want. But a lot of times that's great in the cooling cycle, but it's not so great in heating, right? That creates a draft. The air is warmer than ambient, but it might feel cold against that person's skin. So that can affect comfort. Also, the higher your static is and the more air you're moving through your ductwork, the higher the likelihood is that you're going to rattle the registers and or grills. Sometimes it can be really loud. If you've ever had a customer complain that, it sounds like a truck is coming through their ductwork, you might have some airflow issues. Improper airflow obviously can affect efficiency, especially with ECM blowers. So with a constant torque and a constant volume, right, or what is typically referred to as an X13 motor and or a variable speed motor, the harder those blowers work, the more energy they use. So if you're going from a situation where you've got a permanent split capacitor or a PSC motor in an air handler, and you change that out with a constant volume motor, if your ductwork is undersized, that constant torque or that constant volume is going to use more energy than the PSC that you took out. Not having the right airflow through your indoor coil can cause some issues where we start to send liquid back to our compressor, and that can kill our compressor. We'll talk a little bit about that next week. So I mentioned flex duct a couple of times, and I don't want anybody to misconstrue what I'm saying. I'm not suggesting that we don't run flex. I'm saying if we're gonna run flex, which we are, right, that we run it correctly. And but correctly means you can see this photo that this piece of flex is just completely smashed and destroyed. It says this is 7. There's no way this is this is not a 7-inch round anymore. I don't know what that size would be equivalent to, but it's not a 7. And this is pretty common, right? You look up in somebody's attic, and 9 times out of 10, well, we'll give the benefit of the doubt and say 50% of the time you're going to see something like this. So when we're running flex, any turn or bend in that flex duct, you want that bend to be at least equal to the diameter of, or the radius of what you're running. So if it's a 7, you want that turn to at least be 7 inches round. And you can see I got a little drawing here, or a diagram on the upper left where it shows the diameter of the flex run, and then sort of the diameter of that turn. The larger, the better, right? So the more sweeping turns you can have in your flex run, the easier it is to push the air through. You want those the ductwork to be supported and to have no more than a 1/2 inch per foot of sag between your supports. And a lot of times, if you go and you look, you'll see that there's a lot more sag and a lot more play in a duct run. And then finally, you want that in the internal liner to be pulled as tight as possible, right? Less than 4% compression on that. So you want to pull it very tight. And you can see that at 30%, we have quadrupled the friction rate. At 15% compression of that flex, we've got a 2 times friction rate, and at 4% is where we want to be. And that's pulling that duct really tight. And if you're not doing that, or if you go, I can't tell you how many times I've seen it, and I've done it, where you've got maybe 14 feet of flex in a run that could be half that, and it's just sort of laying up there. If you're having ductwork problems, the easiest thing to do is to find those issues and just cut that extra out, and shorten those runs. Just like the runs, and the hard pipe is the same way too, right? If somebody's using 3 or 4 elbows to get somewhere, that can cause problems too. But it takes a lot more effort to do that than it does with a flex run. Fitting resistance also affects duct system performance. So obviously, the more tapered our transitions and our plenum design is, the easier the air moves through it, right? So when you look at typical versus best, it makes sense that the one labeled best is going to move the air more easily. But obviously, there's a cost difference between typical and best. So typical is fine as long as everything outside of that is run the best that we can run it. Again, each component that air passes through is going to add resistance. That's going to give us a pressure drop, and all of those pressure drops throughout our whole duct system are going to add up, and they're going to affect the static pressure that we're operating against, and they're going to affect the amount of air that we can move through the duct system. In retrofit applications, don't assume that the existing ductwork can accommodate the system that you're about to put in. It's very possible that one of the contributing factors of you replacing this system is because the ductwork was not adequate, and we damaged or killed our compressor because we're not moving enough air. I did not find this picture on a job site. I got this off the internet, but it's pretty obvious that we have a problem here, right? And so one of the things that I like to point out, and this was sort of hammered in my head pretty early in my career, that when you leave a job, whether you're there to do preventative maintenance or you're there to do a service call, you're doing repair, you're doing an installation, whatever you're doing, you're the last professional to look at that job. You're the last one to have your hands on it. You're the last one to do any work there. And the way you leave that job, like it or not, is a reflection on you and or the company that you work for. So if you go to a job and you see something like this where you've got a piece of ductwork that is crushed, or like the previous one, you owe it to yourself and to your customer to fix that. Don't just leave it and say, hey, it's not my problem, because it's very possible that is one of the reasons that you're there, whether it's replacing a blower motor or whether it's the system's not keeping up or whatever, right? So we got to identify these things and we got to fix them. Sometimes they're a little bit harder to see. This one here is pretty obvious, right? You look at this air handler and we've got a ductwork problem. You might not find something like this where I don't know how obvious it is, but we have got a filter grill here, and on the back side of this filter grill, our flex is pulled down so tight at sort of a 90-degree angle that we're really not moving any air through this return. And you might not notice this until you take the grill off, pull the filter out, and really start looking around. And when we start talking about measuring static pressure, we'll sort of go into exactly how you can find this. But this would be an example of when you're checking your static and you're looking at your return static and your supply static. If your return static's real high, you're not moving the air that you need to, and you got to start investigating. But on the flip side to that, you might find a supply run where on your supply static is higher than you would like to see it. And again, you might have to really start looking around and investigating and trying to figure out, it looks like all my ducts are good, but then once you start pulling things apart and looking at it, I took this picture from the internet, so I don't know. I wish I had a photo credit for it, but I don't. I don't know what size this is supposed to be, but whatever size it's supposed to be, clearly it's not, right? You can see that it's got a small little hole punched in the duct board behind it. So again, without pulling things apart and really looking at them to figure out what's going on with my airflow, what's going on with my ductwork, you might not be able to find these issues. So before we move on, friction and turbulence make it tougher for our air, the air that we have to move, right? It's air conditioning. If we're not moving the air, we're not conditioning it. It's extremely important. And the materials that we use, the design and the workmanship of that ductwork has a huge effect on how much air we can actually move. So does it get more important than moving the right amount of air? And we have all the control over that. Now, I get that sometimes all your ductwork is, or most of your ductwork is inaccessible and you can't get to it. I get that. But if that happens, you're going to have to think creatively and maybe, drop a return right there, expand a return if you can. You can't really modify ductwork that you can't get to, so sometimes you have to add ductwork. Before we move on to tools and instruments and measurements, any questions about airflow and ductwork in general? And This is not a duct design class.
No, it's
No
all good,
question.
Wade.
All right, cool. All right, so we're going to talk about instruments required for pressure, air measurements. And we are going to talk about the importance of selecting the right tools and the right measurement techniques, right? So not only is it important to have the right tools, but if you don't know how to use those tools or you're not taking your measurements at the right spot, it doesn't really do you a whole lot of good. So we're going to talk about that. So the measuring device or the tool that we're going to use to measure our static pressure, it needs to measure inches water column in the hundredths, and we want it to go up to at least 2.5 inches water column. And there's a couple different ways we can do that, right? We can do a fluid filled, which is a real old school. That's sort of the one on the upper right, which has got some red fluid in it. It can be an analog, which is that dial, and that's commonly referred to as a magnehelic gauge. Or we can have an electronic, either single or dual port manometer. So when I taught at the technical college, we had fluid filled manometers that the students used, and I'm a big proponent of sort of getting back to basics, and especially or learning with basics, right? I've required all my entry level students to use analog gauges instead of electronic gauges, just because I want to make sure that they understand how it all works, and it's just not a number on a screen. The same thing with the manometers, and the way it works. So this inches water column, we've got figure 2-1, 2-2, and 2-3. So figure 2-1 would be a fluid filled manometer. It doesn't have its ports hooked up to any ductwork. It's just at regular atmospheric pressure, and the red U there at 0 on both sides represents the fluid that's in this fluid or water filled manometer. And you can see it's zeroed out, and we don't have any pressure higher than just atmospheric pressure on either the positive or the negative side. Figure 2-2, we have got a pressure tap in the positive air pressure stream, which would be our supply. And what that supply does, that positive pressure, the pressure of the air moving through the ductwork and then pressing against the sidewall of the duct. Remember, that's our static pressures pressing against the sidewall of the duct. Our tap, that pressure moves through our tap into our piece of tubing and pushes that water down, and that is measured in inches water column. So that positive in our in the diagram here is we have got 3 inches water column on the positive side, right? So we've got our 0 plus 1 plus 2 plus 3. That's 3 inches water column on our positive side. And if we take that same tap and we move it to the negative side, or we move it to our return, where we're pulling the air into the blower, that negative pressure pulls that column of water up in the same amount in this example. So in our figure 2-3, we have got negative 3 inches, or 3 inches of negative pressure. And that's really what we're doing when we're checking static pressure. We're just checking essentially how hard are we pushing or pulling on that column of water, or that virtual column of water if we're using an electronic gauge, or if we're using a dial. The measurement scale is the same, just the way we measure it is different. So here is a magnehelic gauge. or a diagram of one. I think I said 2.5 inches water column earlier. I misspoke. We want to have a minimum of 1.5 inches. You can see the diagram here. This one only goes to 1/2 inch, and that's really not enough to measure most duct systems. A 1/2 inch water column would be ideal. Many out there have static pressure that's far exceeds or much higher than a 1/2 inch static. So there are the magnehelic gauge has a low port and a high port, right? Low port is for the negative pressure. The high port is for the positive pressure. You can measure them both at the same time and it will calculate it. You can measure one or the other. And typically it's good to do this sort of, to do all those. Measure your total external static, then measure your supply, then measure your return, or any combination of those. So you can see exactly what's happening with your return and your supply.
Wade,
yeah.
I got a couple questions, and I think this may explain it right here. But one of the questions was, can you have a negative return static pressure? And I've found with some instruments, they'll read that pressure as a negative number, whereas like your Dwyer magnehelic reads it as a positive number, even though it's negative pressure. So I think that may be where the confusion's coming in, unless you want to elaborate on that a little more.
Yeah. So the return static is always going to be negative because it's on the negative side of your differential. It doesn't really matter though, whether it's a positive or negative, because when we go to add those numbers together to get our total static, we're going to throw those signs away. It doesn't matter. But yeah, if it's on the return side, it's going to be a negative static. And depending on what device you use to read it, it might put a little minus up there. It might not. But it's always going to be a negative. That technically it's always going to be a negative number. Your supply is always going to be a positive number, because remember that the slide that I showed towards the beginning of your air handler with your negative side on the return and your positive side on the supply, that's the same thing that we're looking at, right? We're creating that pressure differential. So yeah, the return's always going to be negative, but it might not show as a negative depending on what tool you're using. But if if it's on the return side, it's a negative. So you want to also, and a lot of measurement devices, a lot of manometers or magnehelic gauges don't necessarily come with static probes. It's usually best if you have them. I recommend them. I have a pair for mine, or actually, yeah, I have a pair. You don't have to have pairs. You can measure, your return and your supply and just add those whole numbers together. But if you look at and I don't know how clear it shows on what you can see, but this static pressure probe is a piece of tubing with a 90-degree bend in it. And the very end of that is capped off. And you can see on this one, on the side that we're looking at, there are two small holes drilled in the side of this static pressure probe. And we want the bend, or we want this to be facing directly into the airflow, with the two sides sort of the two holes pointing against the sidewall of the duct. And that ensures that the static pressure, the same static that's being pushed against the sidewall of the duct, is also being pushed against the side of the static pressure probes. And you can see sort of down here where it shows the airflow, and we got a little pink square around the static pressure tip. That gap there, or that void in this static pressure probe, is supposed to represent the holes. If you just have a flexible piece of tubing, and you take that and you stick it inside your ductwork, it is going to sort of flex or flop down. And by doing that, depending on how it's oriented and where you are in the duct, you might not be measuring static pressure, you might be measuring velocity, or you might be measuring total pressure. So it makes your life a little bit easier if you've got some static probes. Really just the right instrument for the job. And here in this next section, we're going to talk about where to take those measurements. Make sure you got good batteries. If you have electronic, or if you have an electronic manometer, just like you should be keeping batteries on hand for your meter. If batteries in your meter start to die, your meter starts reading all kinds of crazy things. And you got to be able to trust your meter, and you need to be able to trust your manometer as well. If you don't have a manometer, and that's not part of your toolkit that you're carrying around with you every day, you need to get one. I can't stress that enough. You don't have any idea how much air you're moving if you're not checking static and comparing it to the blower table, which I'm going to show you in a minute. So field measurements, we're going to learn how to use the manometer. We're going to check air pressure. We're going to determine static, and then we're going to use our blower data to obtain the cubic feet per minute that we're moving through this ductwork. So what do we need? We need a manometer, we need a static pressure probes, and we need the blower data. So the blower data is in the installation manual that ships with the unit. You can also access all of that information at myruud.com in the PTS section. So you go to air handlers or gas furnaces, and you look at that particular air handler, and go to the INO, the installation and operation manual, and it's in there for all of it. If you don't have a MyRuud account, you need to get with your Tropic Supply Sales Consultant, or talk to the guys at the counter, or ladies at the counter, and they can get you set up. So the first thing that you need to do when you're checking static is you want to make sure that everything's clean, right? You want to make sure that it's got a nice, good, clean new filter. You want to make sure that the blower wheel is good and clean, because those two things will affect your readings. Do not pull the filter out, check your static, and then put the filter back in, because now you have altered that number, right? Because when we check static, we want to make sure that we're checking the static pressure between our indoor piece of equipment and the filter. And if you pull the filter out, check static, and then put the filter back in, you have created a pressure drop by having that filter in the airflow that you have not accounted for, you haven't measured, right? So it always has to be between the filter and the air handler. In the case of a gas furnace with a cased coil, and I know there's not a lot of them in Florida per capita, but there are quite a few. You'll run into them. So you want to make sure that not only are you checking between the filter and the furnace on the return side, but on the supply side, you've got to be checking your static pressure between the furnace and the coil. And I know that there are very few situations where you have got a nice transition like this between your furnace and your coil. But you have to do it, right? You might need to remove a screw or enlarge a hole at the bottom of that coil, bottom of that coil box. Just make sure that you're not putting a hole in your drain pan, putting a hole in your coil, right? Always measure twice, drill once. But if you're not checking, between the filter and your indoor equipment, and in the case of a furnace with a coil, between the furnace and the coil, you're not getting an accurate measurement. Now, it's different with the air handler, because the air handler, the condensing or the indoor coil is part of that air handler. With a furnace and a cased coil, we don't know what coil is going to match or is going to be used in that application with that furnace. So we don't calculate the pressure drop of the cased coil in with the furnace blower data. We do that with the air handler because we know what coil is in it. when it's
We
checking
got a few
static.
questions that I
Yeah.
think I've been typing to the wrong people. So
Okay.
I think I've been answering everything with going to Tim Murphy for some reason.
Interesting.
So one of the questions was on a ducted return, when is negative extreme? My response was that most manufacturers design for a total static pressure of 0.5. So that 0.5 has to be divided, between your supply and return. But we really don't want to go above a 0.5 total static pressure.
So yeah, in a perfect world, right? And I get it. The world is imperfect, but in a perfect world, 0.5 or a half inch of total external static is perfect, right? Which leaves you 0.25 on the return and 0.25 on the supply. Now the blower tables, depending on what motor we're looking at, they might go to 0.7, they might go to 1 inch of static, but that doesn't leave us a whole lot of room for a filter getting loaded up, anything else happening with that system. So yes, in a perfect world, your return static would be a negative 0.25 and your supply static would be a positive 0.25. If you've got a supply static that is, let's say it's, I don't know, 0.1, and you've got a return static that's 0.4, you've got an issue with your return. They should be about equal. Again, in a perfect world, we want to make it as easy to get the air into that blower compartment or into that blower section as it is to push the air out of it.
And then another question was on the probe placement. A couple of questions on the probe placement. So the question was, so the probe needs to be in the air, are you saying that the probe to measure static, make sure it's flat against the wall to make sure the air pushes against it instead of flow in the air? And no, what he's saying is, if you look at that probe, you want to make sure that the holes in the pitot tube aren't in the actual flow of the airstream, or you'll be reading velocity pressure instead of static pressure. So the probes are typically designed at a 90-degree angle. So when you point that 90 degree in the airstream, the holes are actually on the side of that tube and not getting the airflow directly into the holes of that pitot tube.
Exactly.
And then the question was, how would you calculate air handlers on a stand with just a filter? And I replied that you have to drill a hole in the cabinet above the filter and below the coil. And then, they make plugs that you can plug those holes with, or seal them up with caulk or tape or what have you, but, plug those holes when you're finished.
Yeah, you're exactly right. And as far as placement goes, let me expand on that a little bit, because you're always going to have some friction and some turbulence in your airstream. And so when we put together the blower tables and we're measuring static, we are traversing the duct. And really what that means is that, so an example, like both of these pictures that I have on the screen, we wouldn't be taking one measurement. We'd be taking at least 9 measurements, right? So we've got sort of an array of static pressure hoses and tubes where we've got 9 points in that airstream that we're measuring. Now, is that what I'm telling you that you have to do? No, not necessarily. But just remember that the flow of the duct or the configuration of the ductwork before and after where you put your probe is going to affect the air that's going through that ductwork. And if you look, I don't know if you can see my cursor or not, but if you look where on the air handler, the positive or the air handler supply tube is, we're really measuring the air around that particular point in the ductwork. So, depending on how long that tube is, you might want to take readings at multiple points. If you have got a distribution box right, right before that, or if you've got several runs coming into the side of a return plenum, you might want to check a couple of different spots in that plenum, because the turbulence of that particular air, or what they call the laminar flow of that air, can affect your readings. All right, so field measurement here, we've got a pressure tap in our supply. We've got one in our return. You can see that they're both pointing into the flow of the air. You can see that we're checking on our return side between the filter and the air handler. We've got our positive, or our supply, hooked up to the plus on our magnet gauge. We have got the negative, or the return, hooked up to the low port, and on some magnet gauges, these might read as just plus and minus. On some they might say high, on some they might say low. And what it's doing is it is calculating, right? We've got a 0.31, or a positive 0.31 on our supply. We've got a negative 0.19 on our return. And like I said, when you're measuring your external static, your total external static pressure, which is your supply and your return combined, just throw away the signs. It doesn't matter, right? You're adding a positive and a negative, or you're really subtracting a negative from, it doesn't matter. Just add the numbers to the whole numbers together. So 0.31 plus 0.19 gives us a 0.5 static pressure, which is perfect. Awesome. Does that mean that we're moving the right amount of air? No, it doesn't, not yet. And the reason for that is we don't know what blower tap we're using. So the other part of this equation is, when you're checking static, you have to know what blower speed or what blower tap are you using, or you don't really know how much air you're moving, right? So here's a blower table for a PSC motor, and we just measured 0.5 or a ½ inch of static. Well, whether we're on low, right? If we're on low speed, we're moving 1,542 CFM, or 728 liters per second, if you want to use the metric system. We are on high speed, we're moving 1,787 CFM. And the difference between these two is whether we're on low speed or high speed. So that's the other thing that we have to know. We got to know what's our blower speed. We could also measure this if you had a single port manometer, right? Or like I mentioned, it's usually a good idea to check your supply and return. A lot of electronic manometers will allow you to cycle through to display your positive and your negative, or tap A and tap B, or however they have it set up, or however they have it displayed. So you can see, again, we got the same numbers, right? We have a 0.31 on our supply, we have a 0.19 on our return. On this one, we're going to look at a little bit different table. This is from an RH1T, and the air handler that we're using is a RH1T 2417. We have a ½ inch of static. The couple of things I want to point out about not just this air handler, but every piece of indoor equipment that we have has a speed set from the factory. Okay, so this air handler, this 2417, this is pretty common. We ship on high speed, right? So every one of these ships on 5. We don't know what the right tap is for your application. We don't have any idea. So we had to pick something. We pick high speed. They all ship on 5. Well, at 0.5, we have a multitude of CFM values that we might be delivering at a 1/2 inch of static based on what blower tap we're actually using, right? So you see where it says, I got a red box around it where it says motor speed, tap 2 or 3. And then I don't have a box around it, but if you look over the column all the way over to the left where it says model number -H1T, right? So these are all 2417s. We got a 2417 with no heat in a 1.5 ton application. It ships on 5, motor speeds 2 or 3. We have just below that, we have a 2417 with a 13 kilowatt heater, right? So that heater kit is going to add to the turbulence and the friction of that system or that airflow. And so it's gonna change the amount of air that we're moving. So again, there on tap 2 or 3, we're moving different amounts of air. And then at the bottom, we have a 2417 with no heat in a 2 ton application, and it ships on 5. And the suggested motor speeds would be 4 and 5. Now we don't know what your application is. This would be a starting point, right? And so at 0.5, this same air handler could be moving anywhere from 485 cubic feet per minute to 858 cubic feet per minute. That's a huge difference, right? And so we have to pull the panel off and to see what blower tap we are using before we can really determine how much air we're moving. And I will tell you from my experience is that most systems out there today are still wired on tap 5. They always have been. Nobody ever changed it. Nobody ever looked at it. So this is the same example other than the fact that we know we're using tap 5, right? So got a 1/2 inch water column. We're wired in. We're operating on tap 5, 1/2 inch, tap 5, 2417 S with a 2 ton application. We are moving 858 CFM. Okay, so we got 1/2 inch static. We're moving 858 CFM. We're on tap 5, moving 858. Are we good to go? Not yet. We don't know, right? At this point, we know how much air we're moving, but we do not know how much air this matchup calls for, right? I was taught, and I'm sure many of us, I think 58%, I think is what it was, of the people in here have been doing this for 10 plus years. I would wager that all of us were taught 400 CFM per ton. That is not necessarily the case, especially with newer equipment, right? So with newer equipment, we're typically moving anywhere from 325 to 425 CFM, or that's rated, right? So you can get this information from the outdoor unit spec sheet, and that's going to list the most popular matchups, or every matchup will tell you rated airflow at ahridirectory.org. So if you don't know what that matchup is, you don't know what that rated airflow is, look in the spec sheet. If you don't see that matchup in the spec sheet and you know it's a valid match, you're going to have to go to the AHRI directory to look it up. But here's an example, right? So we have a RA 1636. So straight cool 16 SEER 3 ton unit outdoor. When paired with an RH1T 3617 or an RH1T 3621, so that would be a single speed constant torque or X13 air handler, 3 ton, either 17 wide or 21 inches wide. Our rated airflow is 1200 CFM. And okay, say, well, Wade, you just said 400 CFM per ton is not always. That's true, it's not always. For this matchup, it is. right? But for our next matchup, the match with a RH1P 3017, we're looking for 950 CFM. So if we just assume that we're supposed to be moving 1200 CFM through this indoor coil, and we configure it that way without checking to see what the actual airflow, the rated airflow is, we're going to be pushing way too much air through this coil. And our charging chart is not going to be right. You're never going to get the latent capacity, meaning you're never going to be able to get it to dehumidify like it should. It's not going to run the way that it should. It's not going to be as efficient as it should. You're going to have a lot of problems. So you got to know what your rated indoor airflow is for any matchup, and then you can adjust your airflow accordingly. Any questions about that before we move to calculating capacity? And I know we're going a little bit long, but this shouldn't take too much longer. Excuse me.
Nope, all good, Wade.
All right, moving on. So capacity calculation. And Nicole, I will email you this this wet bulb to enthalpy conversion table when we're done here. But there's a couple of things that we have to do to measure capacity. We're gonna check our static pressure. We're gonna compare that static to our blower table because we have to know exactly how many CFM we're moving, not rated airflow, actual airflow. And then we're gonna check some temperatures. We're going to check wet bulb temperature in our return and wet bulb temperature in our supply. So what do we need to do that? We need an induct psychrometer or an induct wet bulb thermometer. And we need an enthalpy chart. And we also need a manometer or a magnehelic gauge so that we can calculate actual cubic feet per minute that we're moving through our dome. We need the chart, which I said I'm gonna email out when we're done. And then we also need a calculator, which is really not a problem anymore because we all have one on our phone, right? So this is the static pressure. I mean, sorry, not the static pressure. This is the wet bulb temperature to enthalpy conversion table. So when we're talking about wet bulb temperature, we're talking about how much heat is in a sample of air, right? And we're going to take that wet bulb temperature, and there is a direct correlation between wet bulb temperature and enthalpy. And what enthalpy is enthalpy is the amount of BTUs in a pound of air. Now, a pound of air is going to be a different volume of air depending on the temperature, but it just tells us how many BTUs per pound of air, and that's what enthalpy is. And so we have to take wet bulb temperature, convert wet bulb to enthalpy, and plug those numbers into our formula. Right. So here's our formula. Write this down. It'll be on the handout, the sheet that I'm going to email. But go ahead and write this down. So BTUs per hour equals CFM times 4.5. 4.5 is a constant in this formula. We're always going to use that. Times our delta H. And the delta H is the difference in enthalpy, right? So BTUs per pound of heat, right? British thermal units, and that's how all of our units are rated, right? And BTUs per hour. We need to know exactly how many cubic feet we're moving so we can plug that number to the formula. We're always going to multiply by 4.5, and then we're going to multiply by the difference in enthalpy. And that 4.5 comes from this table, right? So if you're below 1,000 feet above sea level, right? So if you're higher than 1,000 feet, I don't know where in Florida you're measuring this, maybe on top of a big crane, I don't know, but this is where that 4.5 comes from. It's just a constant in this one. Am I wrong? Is there a place within the state that's 1,000 feet above sea level? So you're going to set up your cooling system. You're going to operate the system in cooling mode, and you want to allow it to run long enough so that we start pulling moisture out of the air. This says operate in cooling mode for 15 to 20 minutes. I would say, I like 30 minutes is a good standard. I like 30 minutes. So allow the system to run for a while. While it's running, you can check your static pressure. You can convert that to CFM. You got your CFM. Once you start dehumidifying and you see water coming out of the drain, then you can measure wet bulb temperature. And we're checking wet bulb. We've got a single return, and then we've sort of got a we've got two supply runs. So we're gonna check on each one of those supply runs and our return. So we got a 55 on one of our extended plenums on our supply. We got a 53 on the other one. We're just going to average those together, right? Which would be 54 wet bulb. And then our return wet bulb is 63 degrees. So what we're going to do is we're going to look at the table. And so on this table, our wet bulb temperature is the column all the way over on the left-hand side, right? It starts at 35 degrees and goes down to, I can't see all the, probably 63, 64. I've got a bar at the bottom of my screen. And then across the top where it says tenths of a degree Fahrenheit, if we had measured, say, 35.5, our enthalpy would be 13.23. It's important to note those tenths of a degree because that will change your formula a little bit. You want to put in the numbers as accurately as you can, right? So in our example, we had a 54 degree wet bulb. Looking at the chart, that converts into 22.62 BTUs per pound. And we had a 63, which is 28.57 BTUs per pound. So we're just going to subtract those two numbers, right? 28.57 minus 22.62. That gives us a difference of 5.95, right? Or our delta H, our difference in enthalpy, is 5.95 BTU. What the heck happened here? So we also had to, I lost a slide, sorry y'all. Okay, so this is using CFM that we've got rated right here. So here's our example, right? We have got a manufacturer's specified capacity of 26,400 BTUs. Rated airflow is 950 CFM. Our actual airflow, which we measured by checking static, we compared the static to our blower table, and we measured 938 CFM. So 938, we're going to plug that into our formula, right? BTU per hour equals CFM times 4.5 times our delta H. So 938 measured CFM times 4.5, which is our constant, times 5.95. And again, we got that 5.95 from subtracting 28.57 minus 22.62. If you forget to convert wet bulb to enthalpy and you put your wet bulb numbers in there, your number is not going to make sense to you. It's not going to add up properly. Then you're going to do the math, and that's going to give you 25,115 BTUs per hour. So right now we measured the amount of heat that we're moving from this system. This matchup is specified at 26,400 BTUs per hour. We're moving 25,115. We're at 95 of specifications. Honestly, we can't expect this piece of equipment to be operating any better than this, right? 95% spec is fantastic. So it may be that it's undersized, right? It may be that it's undersized because we've got some insulation issues. We could have an issue where some windows are cracked. I mean, there's a lot of reasons. If we did the calculation and we came back that we were operating at 18,000 BTUs, well, now we got another problem that we need to look at, right? Did we properly measure and calculate, wet bulb to enthalpy? Are we moving the right amount of air? Do we have a charge issue? Do we have something else going on with the system or with the application? And then finally, total capacity does not equal unit tonnage, right? So and especially with newer and more modern equipment, right? So this is again, we're looking at RA 1636. Depending on what indoor equipment it's matched with, it has a total capacity rating, right? And these are 3 tons, 36,000 BTUs. Matched again with that RH1P, our rated capacity is a little bit less, 35,000 BTUs. But there's two reasons that you need to pay attention to this. One is it can be helpful to know if you're replacing a system, it can be real helpful to know what are you pulling out? What the system that you're pulling out, what is it rated at versus the system that you're putting in, what is it rated at? You could be taking a system out that's rated at 38.5 and putting the system back in that's rated at 35. And that could present some problems. If the 38.5 was barely keeping up, the 35 is probably going to struggle. So it's always recommended that you do a load calculation whenever you're doing a changeout. Some cities, counties, municipalities require that as part of your permit. Some do not. Any questions before we move on to our lightning round?
Nope, you're good.
All right, get your typing fingers ready, everybody.
So open up your chat window, get ready to type. I'm going to ask 4 questions. And
Hey, Wade, there was a question when you were talking about altitude. We do have some buildings in Florida that are over 10 stories. Does that matter?
Yeah, I knew that. And that's why I said, look, I guess if you're trying to figure capacity, right? So if you had a construction crane, right, and those cranes, usually the cab in that crane has a system in it, and you wanted to calculate capacity. If it's over 1,000 feet, you might want to use the 4.37, I think it was. But even then, 4.5 is going to get you pretty close. All right, so first question is define static pressure. So when we're measuring static, we're measuring the pressure of what? Of the air pushing against the sidewall, right?
Yep.
So what is a common instrument used to measure static pressure? If you don't have one, what do you need to get? A manometer, or as my students used to call it, a manometer.
All right.
How many
Magnahelic. Yeah, go ahead.
Or magnahelic would work, sure. But
Yep.
how many CFM are required for a 3-ton HVAC system? So this might be a trick question. It
is a trick question because I'm getting numbers here.
Ah.
Oh, come on. Put your thinking caps on, guys.
How do we know what the rated airflow is for indoor? In the condenser spec sheet. So he is correct.
And
finally,
somebody else said depends on matchup, so that's good too. Another place.
Check the spec sheet for the outdoor unit or go to ahridirectory.org.
All right, we couldn't fool everybody.
All right, so here's this formula for capacity. It is missing something. So BTUs per hour equals what times 4.5 times our difference in heat. So yes, CFM is our answer there.
Good job, guys.
Yeah, fantastic. Any other questions? before we call it a morning.
Robert says you left out Delta Heat on that last question.
Yeah, I have my heat in there, but I don't have my Delta. I don't know, it disappeared.
Thank you, everybody.